others organizing this online seminar series. It's really great. What I want to talk about today is a new way that we developed to measure distance between metric graphs using what we call the persistence-distortion. As this name suggests, you can see that it's going to be built upon a topological idea, which I'm going to detail soon. This is joint work with my colleagues today and students. The central object in this talk, which is a metric graph. A metric graph is basically a length space M associated with intrinsic metric Pm, where M is the line space of a one-dimensional superficial complex G with nodes set V and set E. So basically, we were given a topological graph where every edge is also associated with a length value, basically a positive weight. Then this would give rise to a metric graph as follows. Any edge, since it has a length value, we can consider to be a length metric segment, and we consider its arc length parameterization. If any 2 points, say x and y, in this edge, we consider the distance between them simply as the length of the segment connecting them. And then have a path connecting, say, x and z, necessarily in the same edge. We can make length of this path used by summing up the pieces, the length of the pieces of the graph restricted to every edge. Okay, so this way to define length of a path. Now we can define the geodesic distance, the shortest path metric, which is between x and z, simply the shortest length possible of paths between x and z in this graph. So the metric graph is the underlying space of this graph G and associated with this induced shortest path metric. So sometimes I would just for simplicity, I will simply refer to a graph G as a metric graph with understanding that really the metric space is the underlying space of this graph. Okay. All right. Metric graphs usually occur in many applications in science and engineering. So, for example, very often the data are sampled from a hidden space, which is a metric graph or a metric graph-like structure. Like in this case, we have the GPS position from the hidden domain, which is the road network, which can be considered as a metric graph. Metric graph is one of perhaps the simplest linear structure that can be used to model structures behind data, which goes down the manifold. In this case, this is not clear, but this is basically shows the filament structure extracted to represent the density distribution of dark matter in the universe. So, in order to better use the metric graph as a way to model or summarize data, one important problem involved is to be able to create a metric graph. And that's what this talk is going to focus on. In particular, I want to introduce a new way, so-called persistence-distortion distance, to measure distance between metric graphs, which have some nice properties and can be computed in polynomial time. Firstly, some related approaches. Working graph matching, basically exact graph matching. Namely, you're doing give the two graphs, we're testing whether they're isomorphic or not. In other words, there exists a bijection between the graph nodes, which also induce a bijection in the edges of the two. Okay. Now, for some cases, like when the input graphs are planar graphs or graphs with bounded valence, there are polynomial time algorithms exist for graph isomorphism testing. Unfortunately, in general, for general graphs, this problem is neither known to be in P class or is in NP complete. This is actually one of the popular, famous problems that we cannot really decide whether it's in P or it's NP complete. Okay. In practice, still there are lots of approaches developed to do graph isomorphism testing, usually based on heuristic approaches. In worst case, which may still run in exponential time. Practical application, a more important problem is inexact graph matching. Namely, we don't want to know whether they're exactly the same or not. We actually want to have a distance measured between two potentially weighted graphs. Okay. One is the graph edge distance, which is then labeled some that defines certain edge costs to add one graph into the other, and you want to find the way to convert to the other with minimum aggregate cost. If you think about the where comparing two graphs boils down to find correspondence between graph nodes, so that this correspondence between nodes also make the edges comparable, edges between the graphs comparable. And those edges in each edge involve two nodes. Okay, essentially, typically, to quadratic programming problems, specifically quadratic programming problems. So approaches are based on this IQT programming. Another line of work is using the spectral property of the graph and to measure their distance. And very recently, Hu et al. They developed a so-called classing family signatures to measure how well the edges of the graph correspond to each other. And they also provide several interesting critical property of this Laplace family signature. But very often, this problem to convert inexact graph matching ultimately leads to an optimization problem, which is typically NP-hard. Okay? And in practice, one has to then decide how to find heuristic approaches to use the time efficiency. Furthermore, now, all these approaches, they typically align only the graph nodes. Okay? For example, in this case, the red graph and the blue one, as a space, they're actually isometric. Okay? Saying that they are different discretization of the same metric space. If we align graph nodes, then this two will be very different. Okay? So what we want to do is that we want to be able to align the entire metric spaces of this, the end space of this two input graphs. Okay? If we input graphs as metric spaces, the most natural way to measure their distance is so-called Gromov-Haskell distance, which basically measure how much distance is distorted from one between these two spaces. Okay? So I'm going to give a detailed definition, but roughly speaking, the Gromov distance basically wants to identify the optimal correspondences between points in these two graphs, such as if you take any 2 points, say x1, x2 from the first space, and the distance between them are not perturbed into the distance distortion between them and the distance between their corresponding pairs in the graph G2. You want this distortion to be minimized, the maximum such distortion to be minimized. Okay? It's a very natural way to define, to measure near isometry, to define metric distortion. But unfortunately, the Gromov-Haskell distance is also very hard to compute. Even in a discrete case, and even if the input graphs are trees, or three metric spaces, recently, with collaborator, we have shown that this is hard to compute and even hard to approximate within constant factors. Okay, so instead, we propose a different distance measure, which is using statistical homology. I have several nice properties. First, as I mentioned earlier, we want to align all points in the underlying space, not just the graph node. So I call this continuous distance measure, just distinguish from the one which align graph nodes, I refer to as discrete distance measure. Okay? So this metric insensitive to different discretization of graphs. For example, let's say that we try to reconstruct a road network from noisy data. Different road network algorithms, it could be that one algorithm constructs this very clean node, while the other algorithm constructs this road but with many actual vertices. We want to be able to recognize that these two are the same. Second is that this our persistence-distortion distance also has the stability guarantee, namely, if the input graph are perturbed a little bit, and this metric distortion as measured by Gromov-Haskell distance, then our persistence-distortion distance will also not change much. Okay, important property to have in practice because this implies that this measure is robust to noise, to this type of noise, of course. And that this measure is continuous. It considers all the points in the underlying space of graph. We show that we can actually have a polynomial time algorithm to compute this. Okay. Let me now introduce this persistence-distortion distance. So it's based on a special family of functions, which have the distance function to a base point in the graph. Specifically, let's pick any point S here, this as a base point or the source point. Now there's a function which is simply defined on the underlying space of this graph, which is simply that distance to the space point S. Okay, the shortest path distance to the point S. Okay, so for this function S, and I want to have a way to summarize information encoded in this distance function. And this, we use the so-called zero-dimensional persistence diagram of function. Okay, in particular, so in the middle of this slide, I showed the function value of this the function to the point S, where I take the function value. Okay, basically, what is the zero-dimensional diagram? Oh, here I consider the persistence diagram induced by the super-level set filtration of S. So basically, imagine that with this domain, this graph, top-down, in decreasing function value. Okay, and keep track of the connected components in the portion that we already have. So once to a maximum, like V5, and also U here, each time we pass through a maximum of the distance function, we create new components in the super-level set, which is the portion of the domain, which is above the current function value. And when this component merge at a point, which has this up-box saddle here, like V3 and V2. Okay, and this persistence diagram, every point inside just encode such birth and death event. Like 5 corresponding to a new connect component was created once through the maximum U, and this component merged to another one at a time when we pass through V3 of height 5. It's similarly corresponding to this component, the first aspect of this connect. So this persistence diagram just provides a topological signature of this function to the base point of F. Okay, or we can also say that this is a summary of how does the graph look according to the base point F. Okay, and now we basically perform this for all the possible base points in the graph. So this is 2 collections of persistence diagrams. So all the base points G1 give us a collection pi. All the persistence diagram induced from all base points in G2 give me psi. Okay. So the way to think of this is now, instead of consider G1 and G2, I better map them into space of persistence diagram. Okay, become 2 collection of points in the space of persistence diagram to collect. Okay, now I use in this common space of a persistence diagram, space of persistence diagram, I measure the distance between G1 and G2 as the house of distance between the 2 image sets, pi and okay. In order to measure the distance between 2 persistence diagrams, we use the standard bottleneck distance between 2 persistence diagrams. Specifically, let's say that here we have a set of red persistence diagram, a persistence diagram containing the red point, and another persistence diagram containing the blue point. Okay, the distance between them is simply the best way to one-to-one correspond. The best one-to-one correspondence between them minimize the maximum pairwise corresponding distance, where we also allow some points to be mapped to the cycle. Okay. What we did here is that intuitively, every graph is now mapped to a set of points in the space persistence diagram. Okay. Every point in the graph will give me a corresponding point in the set of persistence diagram. Okay. So the pi and psi are their images in this common space of persistence diagram. This mapping is easy to see that this mapping is isomorphism invariant, namely, if 2 graphs are isometric, then they have the same image set in the space of persistence diagram. Okay, so now measure the distance, the persistence-distortion distance between input graphs is basically measured as the house of distance between the 2 image sets in the space of persistence diagram. Okay. I want to just remark that if remember that for every base point S, we consider the distance function to this base point, and we use a zero-dimensional persistence diagram as a way to summarize the information. Now, we also enrich this information by using the zero-zigzag persistence diagram. Okay, so all the subsequent results I'm going to talk about actually hold for that case as well. All right, that if two input graphs are isometric, then they have the same image in the space of persistence diagram. In other words, this persistence distortion distance, the dPd, will be 0 for isometric graph, for isomorphic graph. We have the following stability theorem, which says that if two input graphs are not too far apart in Gromov-Hausdorff distance, the persistence distortion distance also cannot be too far apart. Nearby graphs under isometry will be mapped to nearby set of persistence diagram, this set of image set in the space of persistence diagram. Okay. So it's not hard. So intuitively, here's just a sketch. Intuitively, what happens is that if we consider the optimal correspondence that gives us the Gromov-Hausdorff distance between the two inputs. Okay, so if you have that optimal correspondence, if you, for any point in G1, if you take any of its corresponding points P in G2, okay, now one can argue that the persistence diagram for the distance function with respect to S, which I denote by PS here, has to be also close to the persistence diagram for the distance function to the base point P, which I denote by QP here. Okay. So in other words, if you just take the corresponding pairs from the optimal correspondences that give us the Gromov-Hausdorff distance, then between any such two pairs, the bottom distance between their resulting persistence diagrams are also nearby. In other words, the unit of S and T in the space of a persistence diagram will be 2 points that's also close by, as measured by bottleneck distance. So to prove this we need to leverage one of the recent results on comparing with graphs developed by Uli Bauer, and myself. Okay. Now, if this isomorphic to G2, then we know the persistence distortion distance between them is 0. How about the other direction? Okay, if it's all true, then we will be able to solve graph isomorphism problem. Unfortunately, this is not true. Here's just one example. I will get into the details. So basically, these three graphs here, what happens is that they're not isomorphic. If you start from a base point, which is outside of them, okay, so basically from a distance, when you look at all the three subgraphs, all of them will give us the same, will generate the same persistence diagram. Okay, so when the base point is outside, we basically cannot distinguish the three. Okay, and now using the three subgraphs as building blocks, one can construct a graph G1 and G2 with certain symmetry involved, and it's not hard to prove that the image space of G1 in the space of persistence diagram is exactly the same as the image space for G2. Okay, basically, these two, the persistence distortion distance will be 0, but these two are not isomorphic. Okay. Now let me talk about the computation of this persistence distortion distance, which kind of the largest part. Okay. Let's simple warm up. Let's look at a discrete case where when I add the input graph to the space of persistence diagram, I only consider those those base points that come from the node set of the input graph, the logical graph. Okay, so we call this two image sets. This image set, we call it the half phi and the half psi. Okay, the discrete persistence distortion is defined as the Hausdorff distance between these two discrete set of images. Okay. Discrete case is not hard to compute it. Okay, so basically we simply need to first compute the two sets of persistent diagrams, the discrete set of persistent diagrams, the image set. This involves that since every graph has only n number of graph nodes, this would just involve computing n persistent diagrams, and this can be done in n log n time. And now we have these two sets, each of cardinality, only of order of m. Now we can compute the bottleneck distance between every pair of them. And so here's a slight twist. So the bottleneck distance between two persistent diagrams can be computed using a general, the Hungarian algorithm, but actually one can modify the algorithm proposed by Exps and his co-authors, which are used to compute the bottleneck distance between two planar point sets, to compute the bottleneck distance between two diagrams in n to the power of 1.5 log n, which is much more efficient than the Hungarian method. Okay? And putting everything together, once we know all pairwise distance between the image sets high and psi, then we can compute their Hausdorff distance in n squared and to the power 1.5 log n time. Okay, this is discrete case, and it's easy. And it's not hard to see that this discrete distance actually provides some sort of approximation of the continuous persistent distortion distance. In particular, we get this relation with this additive error L, where L is the largest length of any edge in the input edge set. Okay, so the discrete persistent distortion distance will be bigger than the continuous one, since we only consider point, and it is bounded from above by the continuous persistent distortion distance plus the larger edge length. And when input graphs are unit, all have a unit edge length, this is an approximation, multiplicative approximation between this continuous persistent distortion distance. Okay. But in general, unfortunately, even the edge length, every edge have roughly the same edge length, but not exactly the same, then this multiplicative constant factor approximation no longer holds. Okay, so in general, it's not clear how to obtain approximation of the continuous persistent distortion distance between input graphs with multiplicative error. Okay, so the discrete persistent distortion gives us additive error with real, because this can be much bigger than the two continuous distortion between two input graphs. Okay. Now, one may think that, okay, then maybe we can try to discretize the input graph, try to make the edge length small, and so that to reduce the additive error. In general, it's not clear how to discretize the input graph so that without adding too many new vertices, adding only the number of new vertices and decrease the length sufficiently small to the level of the continuous distortion between the input graphs. Okay. Basically, in general, it's hard. It's unclear how to obtain an approximation of the continuous persistent distortion distance between G1 and G2 from the discrete version. Okay. So the result that we have is that this continuous persistent distance can actually be computed in polynomial time directly in m to the power of 12 times log n, where m is total number of edges in the input graph and the total number of nodes in the input graph. For graphs that treat the time complexity can be improved to n to the 8th time log n. This is a polynomial time, but this is a pretty large polynomial. What I should point out is that the discrete case, the time complexity actually are comparable to the previous graph matching algorithm, which also only compare graph nodes. Okay, and it's not clear that in general how to expand the previous graph matching algorithm to handle the continuous case. Okay, I will also mention at the end that we believe that this time efficiency here can be further improved. In particular, this factor function that we consider, which is the geodetic function to basepoint, they also very special structure, and hopefully by leveraging those structures further, one can improve the time complexity, bring it down. Okay. All right. So to prove this theorem, it's a bit technical. So in the remaining time, I will just try to give you some level ideas, some of the main ingredients involved. Okay. So the first that let's say first consider one of the graphs G1, and the next one edge is the sigma. In this case, equal to V0, V1 here. Okay. And let's just consider the case when the base edge moves inside this edge sigma. Okay. Now we can parameterize the position of this base point by simply using the arc length parameterization of this edge. Okay. So remember that given the base point, okay, we map it to persistence diagram of the corresponding geodesic distance. Now what we want now as the base point moves inside this edge, because the base point can be anywhere. So as base point moves inside this edge, we want to find out first how does the point in the persistence diagram move. Okay, so I'm going to call this plane containing the persistence diagram. We're going to also refer this to the first step plane, and all the points inside, I'll call them the persistence points. Okay, so basically first we'll understand that to track the movement of this persistence point as base point inside this edge, in the edge. Okay. As the edge moves, we can think of that the corresponding distance function to the base point will also change, and that gives us a time varying function. You can think of the position of the base point to be the time as it changes. We get time varying function. Okay. And the persistent points will move, and because of the stability of the stability theorem of the persistence diagram, the persistent points will also move continuously. Okay. In particular, each of them will choose out a trajectory which is called Wang, which is called a Wang by Cohen-Steiner and Edelstein and Morrow. Okay. The first question that we want to understand is that as to move inside just one edge, okay, how does the one, this trajectory is traced out by persistence points? How do they move? How do we describe them, and what's their complexity? Okay, we know the complexity of all this one. Okay, so like that, this would then help us to understand that as the two base points S move inside G1 and the base point T move inside G2, how does the bottleneck distance, their corresponding for persistence diagram, change? Okay, so let's look at the first step, namely, now in this case, my base point S is going to move along a fixed edge, sigma, and let's just pick one persistence point B, and with burst point E and depth point B, okay, say the 6 here. Okay, we want to know that as S, base point S move inside edge B0, V1, how the first time B, which is 6 at this point, how does this first time change? How does the death time change? Okay, so we analyze them separately. And notice that every point, the B and D, they are generated by a pair of critical points, B and the UD, in the input graph, where the UD that is necessarily a local maximum of the distance function, because that's when you create a new connect component in the super level set, and UD is the upward shadow of the distance function, because that's when two connect components emerge. Okay, so in order to understand the birth and the death time function, okay, we will also track what happens to the corresponding this critical point. Okay, so we'll mainly only talk about the death time function, which is the easier case. Okay, so remember the death time corresponds to a point. because that's where one component merges with another component in the super level set. Now, you can actually see that the saddle point is necessarily a graph node in the input topological graph. Okay? And as the point S moves, okay, the saddle point could remain the same node. Okay, this picture is a space point S moves, then the corresponding saddle point would remain the same node. In this case, the easy to describe is distance function, what happens to the distance between S and the saddle point. Okay, but it could also happen that at some critical moment, okay, base point moves, okay, then the saddle point actually going to swap to a different saddle point paired with the corresponding maximum. Okay, saddle point which generates the persistent point, the death point in the persistent diagram that we're tracking can swap a different one. Okay, but this only happens at a critical moment when intuitively these two saddle points are equal distance to have equal distance to the base point. Okay, so ultimately we can characterize how often such critical events, namely the swapping, can happen and obtain the following result, which says that we're tracking a fixed persistent point in the persistent diagram, and the base point moves. The step time function is a piecewise linear. Step function, namely one value of the time that the component is killed, is a linear function with order of n pieces, and each piece is a linear function with slope either 1 or -1. So it has a reasonably simple characterization. Okay. First time is much more complicated, and part of the reason is because remember the first time when a new component is created, it's based at a maximum, but the maximum doesn't have to be graph node. Like in this case, for space point S, the maximum right now is which is in the interior of some edge. Okay, so it doesn't have to be graph node. First of all, when base point moves, okay, maximum of the distance function of the geometric distance function to the base point can also change continuously. Like in this case, at time x minus, okay, this base point x minus is the local maximum, because what happens is that the distance from S, they're too short. Basically, at the current moment, they're too shortest path between S minus and S minus. Okay, one coming this way, the pi 0, the other one coming the pi 1. Okay, now as S moves to S0, the corresponding maximum also moves, because it remains to at the position where it has two corresponding two shortest paths. Okay, so say, unlike the saddle point, it will not just stay there, it may also move. Okay, so this makes the situation more complicated. But nevertheless, ultimately, one can also show that this first time function has a simple description, which is it is a piecewise linear function with the order of m, more complex than the death time function. So here is order of m, while the death time function was order of n. Has order of pieces, and every piece is a linear function with slope either 1 minus 1 or can also be constant 0. Now, if we put this to the description of the first time function and the death time function together, we got to the following result, which ultimately it says that our base point moves along the fixed edge, which is characterized by from 0 to the length of this edge here. So this is the default coordinate. Okay, this is the temptation of the base point. Okay, and the horizontal plane shows the birth death plane, the plane containing the persistent diagram. Okay, the persistent points inside, they each trace out a 1, and there can only be order of m number of 1 inside during this course. Each of the 1 is a piecewise linear curve with only order of m segments. Okay, description of I move the base point in the persistence diagram. This is how the corresponding, as we move the base point in the fixed edge in the input graph, the corresponding persistence diagram, the points inside, they will follow some curve as trajectory.
Yusu?
Yes?
I'm here.
I forgot to say, the input G1, G2, they also have the topological graph associated with them. So it's the total number of vertices, M is the total number of edges in the input graph. Yes?
Thank you.
Now, know that how does the persistent points move as we move the base point. Okay. So now what we want to do is that using this to help us to understand that while our base point S moves in graph G1, edges in the graph G1, the G1 refers to the edge set of graph G1, and another base point T moves in the edges of graph G2. Okay, we track their corresponding persistence diagrams and see that how the bottleneck distance between them change. We want to get such a description. Okay, precisely, let's a pair of edges, sigma from the first graph G1 and sigma T from the edge set of the second graph G2. Okay, and let the base points move sigma S and sigma T respectively. Now the position of the base point can be parameterized by a point in this ST domain, omega. Every point in this domain corresponding to a pair of base points S in sigma and T in sigma T. Okay. And I'm going to use this function F. You can ignore all the subscripts. I don't know why I put them there. Just think of how we define this function F at S and T to simply be the bottleneck distance between the persistence diagram corresponding to base point S in the first graph and the persistence diagram for the distance function with respect to base point T in the second graph. Okay, so we'll use first, and now this I call this function F the bottleneck distance function. Okay, now intuitively, what I'm saying here is that this function F basically encodes the bottleneck distance between any two possible persistence diagrams in the image set. Okay, now it's not too hard to see that once I understand how this function F, this bottleneck distance function F behaves, we'll be able to compute the persistence distance, distortion distance. Okay, and this function F, okay, 2 points S and T in T domain, which is like corresponding to two base points S and T in the graph G1 and graph G2. Okay, F of ST simply is defined as the bottleneck distance in their corresponding persistence diagram. In that persistence diagram. Okay, so understand this function because once I know the description of this function, and if this has a simple enough description, we'll be able to compute the persistence distortion between G1 and G2. Okay. So let's say here in this illustration, I'm going to use the red point to reference the persistence diagram in PS for base point S in the first graph G1. Okay, and blue point to represent the persistence point in the persistence diagram QT for base point T in the second graph G2. Okay, assume that at some point, this for fixed base point S and T, these are their corresponding persistence diagrams, and what I draw here, what I circled here, are the assumed the optimal one-to-one correspondence between them that give rise to the bottleneck distance between the red points and the blue points. Okay? So now, as we move the base point, as we move the base point S and T, the current persistent points, both the red points and the blue points will move. Okay, and we'll understand that their trajectory will be some polygonal curve. What I draw here, just the projection of the Wang that we talked about earlier. So basically, as the base point S moves, the red point would move, follow some trajectory, and as the base point T moves, the blue point will move following some trajectory. Now, as red blue points move, the bottleneck matching optimal correspondence of bottleneck matching will change. And like here, this blue point used to in the optimal matching, this point is corresponds to this red point. But as the blue point moves up and the blue point is coming this way, then at some point, it's actually we would get a better correspondence if this blue point corresponds. Okay, before such critical configuration happens, the bottleneck matching doesn't change. Okay. And if the bottleneck matching, this optimal correspondence doesn't change, then we can describe this, what happens to the bottleneck distance. Okay, we just need to figure out how often this critical configuration happens and when do they happen and how often they would happen. Okay. And again, it's not too hard to figure out what are these critical configurations. Roughly speaking, when this red and blue points change their correspondences, that means that at the time this happens, you will have, oops, I don't have colors, sorry. This should have colors. Basically, at this point, you would have some red-blue pairs, which are equal distances with another red-blue pair. Okay, so essentially we can basically enumerate all such critical configurations and obtain this this main result, which is that now consider this ST domain omega. Remember the ST domain is simply the parameterization of the two base point S in graph G1 and T in graph G2. Okay, so it tells us that this ST domain omega can be decomposed to a polygonal decomposition of complexity with m power 10 number of cells. So within each of the cells in this decomposition, the bottleneck distance function f that we aim to compute has a simple description. It's just a linear function. Okay, and decomposition as well as the description of f can also be computed in m to the 10 time log n time. So I'm skipping all the details here, but once this is basically the main part. Once we have this result, we get our the privilege theorem that I show you, namely the persistence-distortion distance can then be computed in m to the power 12 log n time, where m is the number of edges and n is the maximum number of vertices in the graph. Okay. So, I will also show you a couple of preliminary experimental results. So first experiment, I just want to see the stability of this persistence-distortion distance. So we take a graph, okay, a lot of points input from it, and we perturb it. We get another graph. Okay, so this is G1. This is a perturbation of G1 called G2. Okay, and see that as we increase this perturbation, as the noise becomes bigger and bigger, what happens to the persistence-distortion distance, which is shown here in the vertical, the y-axis. So here the x-axis is basic noise level, and the y-axis is the corresponding persistence-distortion distance between the two graphs. Okay, so roughly speaking, what we observe is that in general, as the noise becomes larger, the persistence-distortion distance also increase in linear manner. Okay. Now in this graph here, we see this big jump here. What happens here is that, in fact, because the noise at this point is large enough that we can loop here into two loops, which suddenly change the metric space quite a lot. Okay. Example is the following, where we take a collection of surface models. Okay. For each surface, we only use this, the one skeleton of the mesh the of this model. Okay, then we compute the pairwise persistent distortion distance between all this mesh. Okay, those are the corresponding distance matrix, the pairwise persistent distortion distance matrix. Interesting thing is that first note that in this block that I showed here, okay, so these are basically the persistent distortions between similar shapes. So 3 humans, as you can see, we have 3 human models. They are of different poses, but they're roughly isometric, and we see that in persistent distortion distance between them are all small. Okay, and this green group are different centers, and this purple group are different horse models, and this slope is the two walks. So as we can see that within each group, for similar models, okay, just by using the one skeleton of their mesh, apply the persistent distortion between them, can detect that they are close. Okay, and also if we look at, for example, here, this portion between and the source, and the horses, for example, we see that this persistent distortion is still reasonably small, okay, because there's certain similarity between horses and, this is horses and the centaurs. Or also look between wolves and horses. Okay, now if you pick 2 very different shapes, like the kitten model and the armadillo, then you see that persistent distortion distance become much bigger. So this is really just a very preliminary experimental result, but this indeed indicates that this persistent distortion distance measure is first stable and also have reasonable discrimination power in evaluating similar shapes under it allows non-rigid deformation, also differentiate shapes that are not very similar. Okay. In all these experiments show you, we didn't compute the continuous persistent distortion distance because it's too cost and time complexity is too large. So instead, we compute only the discrete persistent distortion distance. Okay, basically, that's all I want to tell you. We introduced this new way to measure distance between to input a matching graph. Which has the first is a continuous measure, namely it takes all points in the space into account, and it's also stable with respect to the metric distortion based on the input graph, and it can also be computed in polynomial time. If we only have discrete case, then the running time is rather comparable to the previous graph matching algorithm. Okay. An immediate future direction, of course, is to improve the efficiency of algorithms to compute the persistent distortion distance, for the exact computation of the continuous case or for approximation, whether we can find efficient approximation algorithm. And this is interesting even for special cases where the inputs are trees, because even for trees, aligning trees computationally, so far it's not such a simple question if trees are unlabeled, namely you don't know the correspondence between their nodes, and no good results for distance between trees at all. At a more broader level, I think it's also very interesting to explore the idea of providing theoretical analysis or algorithmic analysis of using this topological persistence signature for matching purpose. Okay, so here is the topological persistence signature, by which I actually mean a slightly more refined way. Namely, we want to map, we associate such a topological persistence signature for every point in the input space. Okay, and this gives us a map that maps an input object to a set of persistence. A set of points in the space of persistence diagram. Okay, so I should mention that Tuna and the collaborator, they also use a similar type of idea for matching where every point, to a surface matching where every point, the function they consider is the height function instead of the geodesic function that we consider in this work. In general, it would be interesting to provide some theoretical analysis and guarantee of using this such topological persistence signature. Okay, and that's all that I want to say. Thank you all, and I can now take questions.
Sorry, everybody, including myself. If you have any questions, please unmute yourself and ask Yusu. I'll start, Yusu. In the beginning, in your stability theorem, there was a factor of 6 between the persistence-distortion distance and the Gromov-Hausdorff distance between two of these graphs. Is that factor of 6 sharp?
Question, it's not. I think it's so part of this 6 is actually, I said that to prove this, average our results on matching Reed graph and had and I say that no, the 6 doesn't involve that. No, my feeling is this is not tight, but it comes from the following. So in the Gromov-Hausdorff distance definition, one considers the correspondence between points. It's the arbitrary correspondence as long as its position on which the input set is surjective. Okay, so this correspondence doesn't have to be continuous in the way. Okay. In order to relate this distance to the distance between the persistence diagrams, we actually essentially need to establish a pair of continuous maps between the two states. Okay, consider the correspondences induced by a pair of continuous maps. Okay, that's itself in a constant factor. Okay, but what's the right constant factor? Is it a 6? It's not clear to me. My feeling is that's not the case. My feeling is it was more careful Republican height to 4 or something. So yeah, but that's my point because
definitely bigger than 1 is what you're saying.
Yeah, exactly. It's going to be bigger than 1. So.
Yeah, I just have a quick question. You also have a bound between the continuous version of the perturbed distance versus the discrete version. That is, the continuous version is upper bounded by discrete version, upper bounded by the continuous version plus L, where L is do you have any idea about with regard to the rate of convergence, in the sense that where my discretization, I insert more and more points into both graphs and to the discrete version of the persistent distortion? Is there any rate of convergence of approach the continuous version?
That's sure how the rate of convergence is defined, but the following, as you insert more and more points, so additive error is proportional to the largest length of the largest edge length in your current graph. So as you add more and more points, you get this largest length of the length, and then that's the bound. And in fact, I think this bound is potentially tight. In general, since we know the problem is that the continuous persistent distortion distance can be much much smaller than the discrete one. Okay, so say that suppose I want to discretize all the input edges to be so that the edge is very short. Okay, we want to stop. And the continuous distance can be, very close to 0, then they require you to insert a lot of new points, and the number of points you insert has to be bounded by a polynomial of the input side. So that you will not get a polynomial time algorithm. Okay.
Thanks, because that's where I was thinking that whether there's a transition the discrete algorithm to the continuous algorithm, but it doesn't seem to be a feasible direct.
It could be possible. So the general graph is more complicated. It could be possible that for trees can be done.
Thanks.
In your example, you perturbed, in one of your examples, you perturbed a graph that was embedded in the plane. Also a little bit more about how you did that.
The preliminary experimental results, yeah?
Standard way of doing such things, or did you?
Right, the setup for the experiment. This is actually the roadmap of ASIN. Well, simplified version of it. So we sample points from this. See the vertices, but there are actually many vertices here. Okay. Then we assume that now I want to reconstruct this node network. Then for every point, I add a Gaussian noise. Okay. I add a bounded noise. So within certain threshold, say that error sigma, within sigma value, I pick a random value, which is noise value. Okay, point is perturbed. So that you get the point, which is, you see the point, and then I build the Rips complex from the point set as my new graph. So in other words, we consider the one skeleton of the Rips complex to be an approximation of the hidden road network. Okay, this is the graph choose, and then we only get point samples with noise. I build the Rips complex, use the one skeleton of it as an approximation of the network. And then we measure the persistence-distortion distance between the input graph and this one skeleton of the Rips complex.
Okay.
Question.
Yes.
So you were doing all this stuff with the zero-dimensional persistence. Is there any merit to doing all of this with one-dimensional persistence instead?
One dimension, you mean the extended persistence?
I mean, so like looking for loops and things in the graph, yeah.
Right, exactly. So, so you can change the signature to be the one-dimensional. We also add the extended persistence. So all the results on computation remain the same. What will change is that the stability results now have a constant factor of 6, right? In the stability, I say that the persistence-distortion distance is smaller than 6 times the gamma Hausdorff distance there. So this constant will change into 15 instead of 6 if you use the one-dimensional. So this is the only difference. The question is that one can add this for a fixed base point. Adding the loops will give actual information. Definitely. Now, it's not completely clear that now suppose we take all possible base points, does adding the loops still will give actual information? It's not completely clear. But definitely.
Yeah.
Yes.
Cool. Thank you.
Sure.
So that example of two non-isomorphic graphs
Yes,
with
that
the same.
works for both.
Okay.
That works when you include the one-dimensional extended persistence as well, which is like referred to as zero-dimensional zigzag persistence.
All right, questions. Let's all thank Yusu one more time. So thank you very much, Yusu.
You all.
Tune in on Tuesday for our. Thank you, everybody.